Okey, Assalamualaikum warahmatullahi taala wabarakatuh dan salam sejahtera. Uh, Bertemu lagi kita pada kuliah kita kali ini untuk saya menghabiskan chapter 1 bagi subjek Mechanics of Machine. Okey, kita akan yang kita dah study sebelum ni, kita study pasal voice. So last time kita dah study, kita dah mula belajar pasal moment of inertia. Go for the moment of inertia, and then a couple of formulas also has been already been revised throughout. And we also undergo some examples to solve the problem lah. Okay, so if I'm not mistaken, last time kita kita study pasal benda ni saya pick up daripada last time lah. On the last class we do study about the free body diagram of the mechanism. As we can see here, we got the flywheel, okay, where it turns anti-clockwise just in case to lift up the beban, lift up the mass over here. Okay, and as we know, in order to solve the problem, we need to solve it by two cases, where we solve the linear motion first and then we go by the angular motion. Okay, yeah, this one we go by linear motion and then we go by angular motion. Alright, just to recap, as we know, the for the linear motion, the equation is written in this arrangement, where P is equal to mg plus with ma. What does it mean by P? P is the load that acting upward, okay, against the weight of the mass that's going to be lift up. So P, mostly the unit supposed to be Newton lah. So equivalent to mg. M is mass multiplied by g. G is gravity. Of course, G will always acting downward, and the value of the gravity is supposed to be constant. It's consistent throughout, where the gravity is supposed to be 9.81. So we're going to multiply by mass, and mass, the unit supposed to be kilogram lah. Mostly in our case we deal with the kilogram mass. Okay, and then we're going to plus, or we're going to add up with another formulation, another equation, which is mass. Also mass, we're going to multiply with acceleration, which is a. So just imagine, let's say the shaft at the center of the flywheel. So the flywheel somehow rotate anti-clockwise. So we're going to lift up the mass upward. So throughout the process, you're going to generate some acceleration, maybe around 2 meter squared over second. So you're going to measure the acceleration, and you multiply by the mass. So this is how you solve the linear equation or the linear motion of the system. Again, for the angular motion, what our point of interest basically is T, which is torque or torsion. Okay, so what is torsion? Torsion basically is some kind of load. Okay, it's some kind of load where we need to know, we need to quantify what is the torsion needed. Once it rotates anti-clockwise, let's say, in order to lift up the mass here. So in order to get, this is point of interest lah, point of interest. In order to get to the point of interest, basically torsion is a equation that requires you to multiply the I, which is second moment of inertia. I going to multiply with this one, alpha. Alpha basically is the angle, the angle. Let's say is an angle of this is alpha. Is the angle of the rotation motion of the flywheel. This one is a flywheel, Then you're going to plus or you add with the torsion. The torsion friction that against the real torsion. Basically here the value we put it 0, and then we're going to add up with P multiplied by R. P is coming from the linear motion lah. So we know the real P is acting upward since it's going to carry out the mass. But of course, every load going up, every load acting upward, there will always the same load acting downward. So PR basically is you got the same value like P as well. Okay. So this one supposed to be equal to this one. And this whole thing is a free body diagram lah. Need to draw lah the free body diagram. So this is like some kind of, I just recap some steps. I just recap some steps on how to solve this kind of problem. I think it's good for us to have a good standard operating procedures in order to solve this kind of hoist problem. So step in solving the hoist problem, they got couple of steps, which is the first one, we need to draw the free body diagram. We need to draw the free body diagram, and then of course you need to, for this case you need to understand there's a load. There's a load, and we need to know the action of the load. The load is acting towards to what direction. So we need to know the motion of the load lah. Either it's acting upward or acting downward. And other than that, we need to know all the needed parameters. Let's say for our case, we need to show all the forces and the torque acting on the free body diagram, such as linear acceleration, which is acceleration lah. We need to know this one, and then we need to know the angular acceleration. We need to know the torque. We need to know the initial couple of alpha, and then initial couple of acceleration, and then we need to know the torque friction. The torque friction supposed to, this one the value of the torque friction supposed to equal to the real torque. And then we need to know the tension of the rope or cable, and then the torque at pulley from the rope tension, the torque at pulley from the rope tension. And then of course you need to create formula from the linear motion, and the formula is like as we discussed previously. And then we need to know the formula from the angular motion, pulley and drum, and then find the value and then insert all the value throughout the formula, and then you can make a calculation. Alright, So for this case, it's more like an ascending or descending load with acceleration. Okay, as we discussed previously, we got load, either a mass, yeah, a mass of load that either acting upward or downward, and throughout the process it generates some acceleration throughout. So this is the formula that needed formula to solve the problem, yeah. So this example we already discussed in the previous class, but I think it's okay if we recap. We're going to recap the formula again, yeah. So this is the situation, eh? You got 42 kilos of load raising by a rope on a drum. So 42 kilos supposed to be your mass lah, yeah. This one supposed to be mass. Okay, the drum has a radius of 760 millimeter. So supposedly you got a drum, yeah, with a radius of 760 millimeter. Radius of gyration is 360 millimeter and the mass of 50 kilogram. Okay, so 50 kilogram supposed to it refers to the mass of the drum. Here is the mass of the drum. Yeah, if the load move with 2 meter over squared over second squared, yeah, upwards. So this one supposed to be your acceleration. Find the top of the drum to driven the load. So basically the same, the question is more like they want you to know what is the top, what is the top that managed to increase the mass of 42 kilogram with acceleration of 2 meter second. So this is the question. So we already did the exercise in the previous class, and basically in my class it's a compulsory lah for all of you guys to sketch a free body diagram. Yeah, I need to go with the very clear free body diagram. Okay, just a simple like this, and you know where all the variable, the location of the variables, and of course I want to know the value of each variable. And if I really encourage for you to put some notes around throughout the free body diagram of the sketches lah, yeah. So so again, this is how we solve the problem, yeah. As I mentioned previously, you're going to solve the linear motion first, and then you proceed throughout with the angular motion. Okay, for the linear motion, we know the formulation to solve it is just like this lah. So we got P equal to mg plus ma. So we know what is mg. M is, oh sorry, let me erase this whole thing first. Okay, so we know M is equivalent to 42 kilogram. Yeah, G is equivalent to 9.81. Okay, A is equivalent to 2 meter second squared. Okay, so this is parameters lah. So in order to solve it, you just insert all the values variable inside the equation, then you're going to get the answer lah, which is for this case the load is supposed to be about 500 newtons, 500 newtons. So the system is designed to support the load around 496.02 newton at least. Okay, if we solve throughout the linear motion equation. So if we go to the angular motion equation, so this is the formulation. Yeah. So the torque is equivalent to, wait up, the torque is equivalent to PR, which is the rope tension resistance. Yeah, this one PR. Okay, plus with TF, yeah, torque friction, and plus with I alpha. Okay, therefore PR, we knew lah. PR is P. What is P? P is 496.02, and then you're going to multiply with R. What is R? For this case, R equivalent to 760 millimeter. Does it right? Yeah, R is equivalent to 760 millimeter. Let me make it better representation. R is 760 millimeter. Okay, TF for this case, torque friction, is equivalent to 0. Okay, in order to get alpha here we got 2 point, wait up, let me just erase it. Sorry. Okay, alpha we got 2.63, okay, radian per second squared. How we managed to get the formulation? The formula of alpha is over radius. Okay, this one, acceleration over radius. Okay, so from the equation we got the alpha to be 2.63 radian per second. So we just insert it inside in order to get inertia I equivalent to mk power of 2, mk squared. Yeah, m is the mass of the wheel. Yeah, m is the mass of the drum or the wheel lah. This one, the mass is 50 kilogram. This one, the mass is 42 kilogram, something like that. So all out throughout all the equation, then you manage to get alpha is 2.63 radian per second squared, while for the moment of inertia, you got 6.48 kilogram squared. We're going to insert everything inside, and then throughout the equation for the angular motion, you manage to get the torsion to be 3.94.02 Newton meter. So the required torsion here is 394.02. 394.02 Newton meter. That is the required torsion. So if you being an engineer and then you need to design for this case, so with this top, then you're going to select your motor lah. You're going to select your motor and then see how does it go. Okay, that's one thing. Then we go by previously this is ascending, ascending. How to spell ascending? Okay. This is ascending lah, ascending motion. Okay, this case is a descending motion. So how we solve it? Of course, for the in order to make it descend, the movement for the top supposed to be clockwise. It's supposed to be clockwise. Okay, since you're going to how we call it? Since you're going to descend the motion or the load downward, yeah. So they go with the same the formation. I think still the same, yeah, except for this case it's a minus. For the ascending it goes plus, for descending it goes minus, yeah. Why it goes minus? You see here lah, here the P is acting upward. Wait up, let me check. P plus MA equivalent to MG. MG still downward, yeah. Okay, compared to this case, it goes by different thing. Yeah, so I do believe all the arrows is playing a very vital part lah on your study, on in solving the problem. So you need to understand P is acting upward and P always acting upward, yeah. Okay, since it descending, so it goes down, yeah, it goes down. So the area is going downward as well. Somehow if the area is going downward as well, they got a reaction force, which is the mass multiplied by the acceleration. So this is the motion, the motion or the equilibrium of the forces. So if you rearrange, you're going to get P equivalent to mg minus ma. Okay, for this case, since it move anti-clockwise and P still upward, so A is acting upward. So you get what makes different is the MA motion. Okay, since the mass is going upward, so we're going to have the mass multiplied by acceleration acting downward. For this case, the acceleration going downward, so the mass multiplied with acceleration is acting upward. So what that what makes difference lah. I think this one, oh sorry, I think this one is playing a vital role lah in solving the problem. Okay. Okay. That one play a vital role for the whole equation, for the whole equilibrium of equations. Yeah. Okay. Now we go by the third example. This one we go. This is the second example. This is the first example. So the third example somehow shows a hoist drum has a moment of inertia. Hoist drum has a moment of inertia 8,500 kilogram squared. So it got here. It already calculated. Yeah. It already calculated lah. The moment of inertia. So no need to calculate using I equivalent to mk squared. This one already have. We already given. Yeah. And it used to descend. It used to descend a lift of a mass of 1 ton. 1 ton lift. So this one is supposed to be the load lah. The load is 1 ton. And then acceleration is acting downward. It is equivalent to 1.5 meter over second squared. Okay. The drum diameter is 1 meter. Okay. The drum meter. Okay, we got drums here. And then, oh sorry. I'm going to what you call that? I'm going to redraw it again lah. Okay, this is the drum. Okay, the drum diameter. The drum diameter is 1 meter. Oh, check. Is 1 meter. Okay. So the drum is 1 meter of diameter and it goes I equivalent to 8,500 kilogram meter squared. Okay. So now the question is very clear. They want to know what is the torque. So since we know this is a descent process or descent motion, so the torque supposed to be in the movement of clockwise lah. The torque, we don't know what is the torque, what is the value of the torque, but we know the torque is spinning in a clockwise motion. Okay, and then we need to know what is the power required after accelerating for 3 seconds from the rest. So they need to know lah what is the power that required after accelerating for 3 seconds. Okay, so this one is kind of new things lah. This one is new thing. So we're going to see lah how does it solve. Okay, so as we know, we need to solve in terms of linear motion. Then we need to solve it in terms of angular motion. So we know 1 ton is equivalent to 1 power of 3 kilogram. Okay, 1 ton is equivalent to 1,000 kilogram. Okay, in order to get the mass or the weight, of course we're going to multiply with gravity mg, so it goes by 98,000 Newton here. And then we know this is all the given information. We knew that I is equivalent to 85 kilogram squared. Okay, so in order to get the angular acceleration, this alpha, so alpha is equivalent to acceleration over r, which is acceleration is 1.5, isn't it? Okay, the acceleration is 1.5 here. So 1.5 divided by r. Okay, r is what? R is the radius of the drum. The acceleration of angular acceleration supposed to happen in the drum. Okay, so since the drum got 1 meter of diameter, so you want to solve it in terms of radius, so it goes by 0.5 meter, this one 1.5 meter over second. So you got lah 3 radian over second squared. Okay, so all the information you gathered all together and then you solve it throughout the linear motion. Since this is ascending, this is descending, so dia menurun ke bawah. So the mass multiplied by acceleration is supposed to be in a negative direction. This is what makes it different. Of course, the first step. First step is to draw free body diagram. This is the most important. Okay, so just imagine you got load here 1 ton. Wait up. Okay, it's a 1 ton of mass. Okay, it descend downward. So if it descends downward, of course here we got mg lah. Since it descends downward, so A also going downward, so we're going to have a reaction force of m object of m a. Okay, and then we know here is P. Okay, so P plus MA equivalent to mg. Okay, why P plus MA? Because P is acting downward, MA is acting downward, mg is acting downward, so that's why it's supposed to be on the other side. So if we manage to rearrange back the equation, so we're going to get P equivalent to mg minus ma. So there you go. Okay, this is the whole fundamental of the physics. So that's why I said the direction is playing very important part lah for you to solve the problem. Okay, so inserting all the values is very easy, and then you calculate the whole inserted values here, then you manage to get the load to be around 8310 Newton, 8,310 Newton. Okay, so now we're going to solve for the angular motion. You cannot solve the angular motion without solving the linear motion first. since all the what you call that, the input for the angular motion is came from the linear motion. So the formula for the angular motion is T, and the torque, the torque torsion equivalent to IA, inertia multiplied by angular of acceleration plus with torque friction, and then minus with PR. Why it goes minus with PR? We can check here. We see PR, it goes minus here. Yeah, since T, it go here. If we check here, torque plus with PR. So torque, everything acting downward, plus PR. So this one is downward. Okay. IA is here. IA it against this motion. And then same goes with, since we know the torque acting like this, of course TF acting in opposite direction. So this is happen to be the formulation. Yeah. So if you know how the load is being arranged throughout the the process, then you kind of know lah how it's solved. Let me show you again how this equation is derived. We know that torque is acting anti-clockwise since it descends. Yeah. So basically, force down. What is the force down? The force down is torque and T R, the rope tension. And then we go by force up. What is the force up? Kind of like anti-clockwise. So we got I alpha, and then we got T F. So we just rearrange it that way. So T plus PR equivalent to I alpha plus T F. So rearrange balik, and you got this equation lah. So same goes to our case here. What changes is this one. Yeah, the tension of the rope tension, the rope resistance, to be precise. So from this case, you're going to what you call that? You're going to insert lah. I, you already know, is 85 kilogram meter squared, multiply with 3, which is the angular acceleration, plus with torque friction, of course 0. Okay, and then minus with PR, or the rope resistance lah, kind of. So P is 8310, 8310. So here we go, multiply with R. R is the radius of the flywheel. Since we know the diameter of the flywheel is 1 meter, so 1 meter divided by 2, we got 0.5 meter. So from this case, you manage to get the torque to be 21,345 Newton meter here. Okay. And then of course they want to know what is the power. This power basically for motor selection. What you for motor, ay. Oh, it's been too sensitive. This one is for the motor selection. Motor selection. Okay. The power, the formation for a motor selection is P equivalent to torque multiplied by omega. Okay. So how are you going to get the omega? Omega is the formulation for omega is omega equivalent to velocity divided by radius. How to get the velocity formulation? The velocity is equivalent to acceleration multiplied by time. Acceleration is 1.5, isn't it? 1.5 meter, 1.5 meter squared supposedly. Okay. Then you're going to multiply by t, which is 3 seconds in here. If I'm not mistaken, yeah. You already stated the condition for 3 seconds from the test. So you go by 1.5 meter over square second multiply by t, which is the second. So in here it goes by meter second squared multiplied by second. So you got meter squared. You got 4.5 for the velocity, and then 4.5 you put into the equation of omega equivalent to velocity over r. Okay, and up you manage to get the omega to be 9 radius per second. Omega is the velocity of the angular motion. Alpha is the acceleration of the angular motion. Two different things and two different quantity. So you need to be very careful on that. So once you manage to get the omega, which is 9 radius per second, so you're going to equate in the equation, power equivalent to torque multiplied by omega, which is for our case now we got 21,345 multiplied by 9. Yeah, 21,345 Newton meter. This is Newton meter multiplied by 9 rad per second. So you manage to get the power to be 192.11 kilowatt. So the motor selection is supposed to be on this specification. Motor power. Okay. For you being engineer, you have to select what the suitable motor to support this kind of cases. So for this case, the motor is supposed to be around 192 kilowatt in order to support a weight about 1 ton. Maybe if you considering some safety factors, maybe you can increase it, the motor power to be around 200 kilowatt. Of course, the motor itself got different ranges. It comes in variations. So maybe at around 150 to 200, or maybe you're going to push more. So you go by 200 kilowatt, then it should be okay. So the recommendation motor is supposed to be around 200 kilowatt, considering some safety factors around maybe a quarter of the power. Let's say 3/4 multiplied by power. So this one is safety of factors. So in case there will be a loss of power somehow, there's still some backup. Of course, for this kind of situation, in standard engineering design, you're not going to rely on one power. It need to comes with with at least basically they will design it to be 3 motors, and you're going to alternate one motor, and the first and second motor will be alternating on each other, and then you're going to be back up with the jockey motor. Okay, so this is the standard design that need to be considered to designing a lift system, yeah, for a building lah. Okay, so we done with the descending part. Now we're going to go for the example 4. Okay, for the example 4, you see a 5 ton of mass has to be raising by using a lifting machine with acceleration of 1.2 meter over second squared. So 5 ton, you go by 5 ton of mass. So this one supposed to be load lah. Okay, that you need to raise. So different, it got different terms. This one raising, mengangkat, and this one is descend, menurun, and this one another one is ascending, menaik, naik. So another example for case of raising load using a lifting machine. Of course, they got the acceleration. Acceleration is 1.2. This one is A lah. 1.2 meter over second squared. The drum of machine has a mass of 1.5 ton. The drum of the machine means so you got what? 1.5 ton. 1.5 ton of mass for the drum, and then the diameter is 1.8 meter. The diameter is 1.8 meters, and the radius of gyration is 630 millimeter. Calculate torque lah. Calculate torque is required. Raising the mass lah. How much power was produced after the mass moved for 5 seconds from the rest? Given friction at drum 1.9 kilonewton meter. So now by this time they already include the friction. So they managed to calculate some friction here and there, so it managed to give some value to be around 1.9 kilonewton meter. Okay, for the friction. So how we want to solve this problem? So this is the free body diagram. Okay, since we know it's a ascending, a raising sort of motion. So the torque supposed to be anti-clockwise. So this is the torque. We don't know what is the torque, but we know the torque is moving eastward. This angular motion of anti-clockwise. Okay. Since we know there's some what you call that? There is some acceleration acting upward. Acceleration acting upward. So there will be a reaction acting downward, which is m multiplied by a. So by this time, it's going to be PR. So by this time, mg plus ma, and then equivalent to p. Okay, isn't it? Yeah, mg plus ma equivalent to p. So here lah. Then you insert all the equation inside. 5 ton is equivalent to 5,000 kilogram, and then you multiply by gravity, which is 9.81, and then you plus with 5 ton multiply by acceleration, which is 1.2. This one is acceleration, meter square second. Okay, then you manage to get the load to be around 55,050 Newton. Okay, so by right you're going to solve it throughout the angular motion, the second step. So torsion is equivalent to I multiplied by alpha, the acceleration of angular, the angular acceleration, plus with PR, and then plus with TF, torsion friction. So we know the friction at drum is 1.9 kilonewton meter, so that's why we equate this one. Okay. At the same time, for this case, we know I is equivalent to mk power of 2. M is the mass, K is the radius of gyration. So you're going to equate all the equation, and you manage to get it about 595.35 kilogram squared here. And then you're going to multiply by the angular acceleration, 1.33. Angular acceleration is like this, acceleration over radius, then you got 1.33 here. Forget about this. So you put here, and the P load is multiplied by radius 0.9. Why 0.9? Since the diameter of the drum, the diameter of the drum is 1.8 meter. So that's why you divide it by 2, then you got 0.9. So everything is already given, not much. Then if you put all the equation throughout your calculator, then you manage to get the top to be around 52.239 kilonewton meter. This one. Very simple one. And since we know they do ask about what is the power, so the power is equivalent to torque multiplied by multiplied by omega. So in order to get the omega, you have to find the velocity and so on and so forth lah, here. This is all the step required to get the omega. So omega is equivalent to velocity over radius. How to get the velocity? You need to convert it from the acceleration over time, so you're going to multiply by time. Here, does it give you some times here? Here, how much power was produced after the mass moved for 5 seconds? 5 seconds. The mass was moved for 5 seconds. So you already give 5 seconds, right? I don't know why they put 3. Supposedly this one is supposed to be 5. So if you replace it to from 3 to 5, then maybe this one going to be different lah. And then this one going to be different, and it's going to be a bit different lah. Maybe a bit higher, maybe 5 radius, 5 rad per second. Then going to multiply by this, and then the power will be around the corner lah. So this is how you solve the problem for the ascending situation, and you know where to get the power and so on lah, Okay, so I've done for that part. On the next class, we're going to go for the situation of ascending and descending load with uniform velocity. Yeah, the velocity somehow is designated to be quite uniform lah. Yeah, maybe there will be some changes. What for that? There may be some changes here and there throughout the way or the procedure in calculating the equation. Yeah. So on the next class, we're going to through this ascending and descending load with the uniform velocity, and then of course we're going to study on the condition of free fall. This is the worst case scenario lah. This one is the worst case. Okay. Means they don't have any friction and so on. Just imagine that the rope is somehow broken lah, and tali cable putus, so the load jatuh macam tu je, free fall. What will happen after? Alright. Okay, they got some example lah here and there. Okay, couple of example, and then we going to go with balancing mass here. Okay. So at this moment, I stop at ascending and descending, and then we covered a bit of acceleration upon time, and then we do study about the power. Okay, we of course cover some powers for the motor, and that's all for now. Okay, I mentioned previously on the next class, Thursday if I'm not mistaken, we're going to study on the ascending and descending motion and load with uniform velocity. Yeah. So until then, thank you very much, and Assalamualaikum warahmatullahi wabarakatuh.